Okay, so let's talk about some higher derivatives. So since the derivative of a function f of x is another function, f prime of x, what's to stop us at taking the derivative again? That is the derivative of f prime of x. What would that look like? What could it tell us, and how can we notate it? So if we were looking at this, the first derivative of a function f of x is denoted by f prime of x, and that's just going to be taking the limit as h approaches 0, we've already learned this, of x plus h minus f of x all over h. If you looked at the second derivative, that's going to be taking your first derivative function and doing the same thing. Limit as h approaches 0 of f prime of h, because you're taking the derivative of the first derivative. So the second derivative is the derivative of the first derivative. What do you think the third derivative is going to be? That's going to be the derivative of the second derivative. So that's going to be the limit as h approaches 0 of the second derivative. So we'll get that. So let's go back to this ball problem that we did in the last section. A ball is launched vertically into the air from the ground with an initial velocity of 96 feet per second. Its height, s of t, equals 96t minus 16t squared. Find and interpret the first and second derivative, then interpret the results in context with units. Okay, so if I were to find that first derivative, so that first derivative is going to be taking the limit as t approaches, or as h approaches 0 of s of t plus h minus s of t all over h. So if you go back to the last section, we actually did this, and we ended up finding that the answer to this was 96 minus 32t when we went and expanded that whole thing out. Okay, so there's our first derivative. Okay, so first derivative, it's going to be, again, it's the change. If I'm looking at my units, we've got the y values are going to be the feet, so it's the height. The input values are the t, which is the second. Okay, so this means the velocity function for the ball is 96 minus 32 feet per second. If I were to find that second derivative, so now that's going to be taking the derivative of the first derivative. So this is going to be the limit as h approaches 0 of s prime of t plus h minus s prime of t all over h. So that gives me the limit as h approaches 0 of 96 times t plus h minus 16 times t plus h squared minus 96t minus 16t squared all over h. Now again, I'm going to remind you, we actually went through and did all of this in the last section, so or previously. So if you go back to that, you'll see when we did that, we ended up getting 0. So this again, here's our acceleration formula. So this says, if we were looking at this, our change in y, so here our output values are in terms of feet per second. And then our input values, again, is that t, so that's per second. So feet per second is going to be, so acceleration is constantly 0 feet per second squared.